Halfway through the semester. Here we go. So, what we've done so far is use some big calculus tools to compute a lot of things. We started off with limits. We used limits to build up the idea of continuity, which was important even though we only talked about it very briefly. And then we used the limit to build up the definition of what a derivative was. Since then, we've really focused in on the derivative, and we've started mostly trying to find some computational tricks and tips and hints and shortcuts and things like that to help us come up with derivatives easily. We talked about product rule, quotient rule, chain rule, all these different rules to come up with the derivative of different types of functions without having to use that limit definition. What we want to do in this unit is start focusing in on what the derivative actually is and what it tells us, specifically what its application is to a graph of a function, what it tells us about the graph of a function. So we're going to start off by talking about the first derivative, and we first want to just kind of understand what the first derivative means. If I just asked you to find the first derivative of this function, most of us would naturally go ahead and say f prime of x equals 24x cubed minus 6x. Ooh, well, let me fix that. That's pretty ugly. There we go. 6x, and we might say plus 0. We might just leave that constant off because we know that that constant's derivative is going to go to 0. Now, if there's a first derivative, there's also probably a second derivative. So, without having to think too hard, my guess is that most of you would say that the second derivative would be 3 times 24, that's going to be 72, x squared minus 6. And notice that we've just put two little tick marks here. We could call this like f double prime. And then we could find the third derivative after that with 3 tick marks, and we'll bring that that exponent down in front of the coefficient and make that 144x minus 0, but we'll leave that. And we could do a fourth and a fifth and etc., etc., etc. After the third derivative, we start using Roman numerals instead of tick marks. A lot of times people will put it in parentheses like that. Eventually, when you deal with fourth, fifth, sixth derivatives, we don't want to have to throw in all those tick marks. And we can figure out this kind of thing like that. Now, we're only going to focus on the first derivative and the second derivative. But if you remember back to our first interpretation of the derivative, we said, like, if this function was a distance function, then the derivative of distance would be velocity. So we say that velocity is the first derivative of distance. And then the derivative of velocity is acceleration. So acceleration is the second derivative of distance. So we're going to focus on first and second derivatives mostly and try and figure out what they mean, what they tell us. Right now in this video, we're specifically going to focus on the first derivative. So we're going to make the connection, or we're going to remind ourselves of the connection between the derivative and slope. We know, before we get into this little theorem here, that the derivative is the slope of the tangent line. So, when we think about slopes, we can think about the sign of that slope, what it means if the slope is positive, what it means if the slope is negative. We know that for linear functions, if the slope is positive, it looks like this. And if the slope is negative, it looks like this. What we're going to do is just start connecting these positive and negative slopes to when functions increase and decrease. So that's all this theorem says. If we've got an interval of x values and the derivative is positive on that whole interval, even if it's different positive numbers, what that means is that the slopes are always positive on that interval. And so we'll say that the function f is increasing. Our old definition for increasing was probably something like, as you move left to right, your function goes up. It's pretty vague. It's pretty ambiguous. It's not very rigorous. Now we can define that using this positive derivative. Similarly, we'll say if the derivative is negative, that means the slope is negative, and so your function is going down, it's decreasing. All the tangent lines are going to have negative slopes on there. If the derivative is equal to 0 on the whole interval, that means the slopes are equal to 0 for all the x values on that interval, meaning at every point you've got a horizontal tangent line. So really what we'll notice is that the graph is a horizontal line. It's constant. So this little theorem just kind of shores up our connections that we've normally made between positive slopes and negative slopes with a function being increasing and decreasing. So we can take a look at an example and try and mess around with this and see what's going on. If we want to find out where this function is increasing or decreasing, we're going to be looking at where the derivative is positive or where the derivative is negative. And if we want to find horizontal tangent lines, we know that we're looking for x values where this derivative is equal to 0. Now that's different than just having a constant function. Because here, for our function to be constant, the derivative needs to equal 0 on this whole interval. With horizontal tangent lines, they could show up on an interval where our function is constant, but they could also just show up at a single point, not on an interval itself. So we're going to find all the spots with horizontal tangent lines, and maybe let's do that first. So we know we're going to try and find where the slope, the derivative, is equal to 0. So for this function, let's first find the derivative. Let me just do that over here so we've got it on hand. 8 minus 2x. Not very difficult. Now we can go ahead and figure out where this thing is equal to 0 pretty easily. So maybe for our horizontal tangent lines, h tangent, we're going to say 8 minus 2x is equal to 0. That means 8 equals 2x. So if we divide both sides by 2, we've got a horizontal tangent line showing up when x is equal to 4 on this graph. If we want to show where the function is increasing or decreasing, we're really looking at where the derivative is positive or negative. So if you want, we could go ahead and set up some inequalities. For increasing, we're going to find 8 minus 2x is greater than 0, and we're going to solve that. And for decreasing, we're going to say 8 minus 2x is less than 0. Now, what you might remember all the way back in continuity is that when we solved inequalities, we didn't just solve them using algebra. In this case, it's pretty easy to do it. You can add 2x to both sides, and we've got 8 is greater than 2x. You can divide by 2, and you've got 4 is greater than x. Or if x is less than 4, what that means is negative infinity to 4. That's where this thing is increasing. When it's decreasing, we're going to say we'll still add 2x to both sides. We'll still divide by 2. So we have 4 is less than x, or x is greater than 4. That's the interval 4 up to infinity. That should make a bit of sense because we know what this function looks like. This is a parabola that's upside down. The sketch of this should look something like this, where this is an x value of 4 because we've got that nice horizontal tangent line there. That's what we found. And then it increases on the left of that, and it decreases on the right. Increasing, decreasing. So from negative infinity up to 4, it increases. From 4 up to infinity, it decreases. But we can find that by solving these inequalities. Now, these inequalities are pretty easy to solve by hand. We just had to add 2x to both sides and divide by 2. But if you remember back in continuity, we had some strange rational functions, and they were harder to solve inequalities where they were greater than or less than 0. So we did the whole partition number sign chart thing. That's going to come back. We're going to be doing some of that to solve these inequalities. What we'll do is we'll solve these inequalities here at the same time by building a sign chart in the exact same way that we did. So to do that, I got to get you the definition here. We're going to talk about critical numbers. A critical number is a real number x in the domain of f such that the derivative f prime of x is equal to 0. Notice this is a horizontal tangent line. Horizontal tangent line. Or the derivative does not exist. If you remember, that is either a sharp corner or a vertical tangent line. Now, it could be other things, but we'll talk about that later. Those x values, those are called critical numbers. Sometimes we'll talk about critical points. If the x value is the critical number, then the actual point, x comma y, is the critical point. So if c is a critical number, you just plug that into your function to get the corresponding y value, and that's the critical point. Not a big jump there. People typically just use these interchangeably. If you want to talk about a critical number or a critical point, sometimes they'll just give the x value. I'm not going to be terribly picky. If I want you to find a y value, I'll tell you specifically, find the y value that goes with it. So you might recognize this definition. What we'll notice is that critical numbers are in the domain of f. That's part of it. But they're partition numbers of f prime. If you remember back in continuity when we talked about partition numbers, we said that they were where a function was equal to 0 or was not continuous. Now, we're switching that out for the does not exist part here, but it's not going to be much different. So our goal is going to essentially be to find the partition numbers of the derivative, which, if I go back a slide, makes sense because to solve these inequalities, to set up a sign chart, we would use a partition number. We found that one here. That's where the derivative was equal to 0. And we set up intervals around there, negative infinity up to 4, and 4 up to infinity. Then we could just test these intervals and see if they're positive or negative. And now keep in mind, we're testing the first derivative, so we're really seeing if it's positive, that's where our function is increasing. And if it's negative, that's where our function is decreasing. So that sign chart is going to be really helpful. But partition numbers are not the main important thing. It's these critical numbers. So everybody always asks, what the heck is the difference between a critical number of f and a partition number of f prime? The only difference is that the critical number has to be in the domain of f. So sometimes we'll get partition numbers of f prime that are not critical numbers because they might not be in the domain of f. An easy example is something like where a function has a vertical asymptote. The function won't exist for a small point there. If there's a vertical asymptote at x equals 1, for instance, f of 1 won't exist. The function does not exist at that point. But notice also the derivative won't exist. So f prime won't exist there. It's not a sharp corner or vertical tangent line. It's because our function doesn't exist. We've got some discontinuity going on there, all that kind of stuff. If the function doesn't exist, we don't really care about that. Notice the critical point part kind of gets around that because we just see what the y value is that goes with it. If it has a y value, it's critical. If it doesn't, if there's something else going on there, like a hole or a vertical asymptote or something like that, if it's not in the domain of f, then it might be a partition number of the derivative, but it's not a critical number. Very small distinction, very important distinction. Come back to that difference every now and then just to remind yourselves because it's easy to mix that up. All right, so here's our example. Let's find critical numbers of f, and we'll find the intervals where it's increasing and decreasing for this function. I'm going to use a sign chart to do this. We're going to kind of do a full little first derivative analysis. So before we do any of that, we need the actual derivative, f prime of x. You might notice we have some chain rule going on here. See, we're going to have to be up to date on all of our derivative rules. We've got this 1 minus x inside of our box. So if we bring our exponent out front, we put our box here. We're going to subtract 1 from our exponent to get negative 2/3. And then we're going to multiply by box prime. If I fill everything in, I've got 1 minus x. Oops, I put negative 1x. That's not what I mean. There we go. 1 minus x in our box. And the derivative of this is negative 1. What this really looks like is negative 1 over 1 minus x to the 2/3. That's my derivative. Now, what we want to do is find partition numbers of this thing. We can do this in the same way that we did with continuity. We're going to look at the numerator and see if there are any x values that make the numerator 0, because that's the x value that would make our derivative equal to 0, because if it sets the numerator equal to 0, it sets the whole thing equal to 0. There's none there because we just have that negative 1 fixed. But we'll notice that if you put in 1, we've got this f prime of 1 does not exist. So maybe we've got a vertical tangent line or a sharp corner or something like that happening here. But that's going to be a partition number of the first derivative. We should check, is it critical? Again, the main thing to check for is, does f of 1 exist? If you put 1 into your function, is that an actual point? Is this x value in the domain of our function? Sure enough, if we put it in here, we get 1 minus 1, that's going to be 0. 0 raised to the 1/3 is 0. f of 1 equals 0. So check, this thing is critical. If we got that when we put 1 into our function, we maybe divided by 0 or something like that, and we got some non-existence, then we'd say it's not critical. Now what we can do is set up a sign chart. So our x values are going to be set up in intervals from negative infinity up to 1, and from 1 to infinity. Just like we would splitting things up around our partition numbers. Now, every now and then, what I'll do is I'll put the actual critical number, the partition number, in here. You'll see why in a second. Then I'm going to plug these test values. Notice I'm going to plug them into the derivative function, not the actual function that we had. The reason is, if I go back, I want to find where our derivative is positive or where our derivative is negative here. So I'm trying to check the sign of my derivative. So here, if I plug in 0, let's say, into our derivative, I get negative 1 over 1 minus 0. That's going to be 1. So I get negative 1. That is going to be negative. If I plug in something bigger than 1, like let's say 2, then I get negative 1 over 1 minus 2. That's going to be negative 1. But when I raise it to the 2/3, it becomes positive 1 again. So now I've got negative 1 over positive 1. That's going to be negative. What that means for my function is that if my derivative is negative, my function has to be decreasing because the slopes are negative. I use a little downward arrow to represent that. Same thing here. On this interval, we're going down. Now, every now and then people will say, well, wait a second, what's happening in the middle here at this x value of 1? Every now and then I'll put something like does not exist in here just to remind me of what type of critical number it was. Because there are two types. There are two types of critical numbers because we're looking for where the derivative doesn't exist or where the derivative is equal to 0. That's going to just be a helpful little bit of analysis later on in this unit. So I maybe will start throwing it in there. Don't worry too much about why we're doing that yet, but it might give us some clues as to what's happening visually here. So if we're trying to find critical numbers, we've got a critical number at x value of 1, and we've got that our function is decreasing on this interval from negative infinity to 1, and it's decreasing from 1 to infinity. So, wrong one. So what I might do is say that stuff. Let me write it up. So the critical numbers, I thought I had a summary slide after that. The critical numbers are x equals 1, and then we've got that this thing is decreasing on negative infinity to 1, and from 1 to infinity. Every now and then people will join these up together and say that it's decreasing from negative infinity to infinity. We have to be careful about that. In this case it is, but I'm not going to really split hairs too much, so if you want to just list the separate intervals, that's good with me. Yeah, there's some cases where it won't happen like that. If our function doesn't exist in the middle, even though it does in this case, then we'd have to split the intervals up. So I think it's always just safe to leave it. We're decreasing on both of these intervals, and it's never increasing. So that's what this function looks like. We can kind of visualize it a little bit, but if you want, take a look at the graph of this function. Just put it in your graphing calculator. Make sure it makes sense. Make sure it actually is decreasing from negative infinity up to 1, and then from 1 to infinity. We'll do another example here. Find critical numbers and increasing, decreasing, all that kind of stuff. So we'll say f prime of x. You've got some options for how to find the derivative. I'll let you mess around with this. Pause your video, give a shot to this, see if you can find the derivative. All right, if you're doing this, a lot of people probably used quotient rule. I'm an anti-quotient rule person, so I would rewrite this and then use the chain rule, but that's just me. If you do the derivative, you're going to get negative x minus 2 to the negative 2. Either way, it's going to look like this. So here's your derivative. If you didn't get this, go back and check it. Do the quotient rule again. Do the chain rule. Here you go. Try and figure it out, but make sure that you end up with this as your derivative. So we need to find partition numbers of the derivative here. And again, once we've got it set up in this quotient, it's not hard to find. There's only one. It's an x value of 2. We should check, is it critical? Take a second. You answer that question for me. No, this is not a critical number. The reason is because if you plug 2 into this function, it does not exist. Notice that the derivative is allowed to not exist. But here, if we plug it into this spot here, we're going to end up with 1 over 0. What we'll notice is that actually there's a vertical asymptote going on here. You've got a vertical asymptote happening at the x value of 2, and that's why the derivative doesn't exist there. Why do we care about that part? Why is it, critical or not critical or whatever? It doesn't really matter right yet. We're going to get into that later. We'll notice that critical numbers serve a really important role. You'll see that in this video. But for now, don't worry about it. So we'll do our sign chart now. Notice that this is still a partition number, and so we're still going to use it to split up our intervals. But now what I might do is put a little star here. That just means like, hey, this isn't a critical number actually. Remember, it's not a critical point, and so when we have to do analysis later on, we shouldn't get too tricked into it. What we can do is check out the signs of our derivative, and we'll see what that tells us about our function. So again, go ahead, take some test values from these, plug them into the derivative, see what you get, and we'll see what happens. All right, turns out this is a boring example because it's a lot like our last one. No matter what you put in, this is going to be negative and negative, so that means our function is decreasing and then decreasing. So if we wanted to answer this, for the critical numbers, we've got none. For the intervals where it's increasing, we've got none. For the intervals where it's increasing, we've got 2. From negative infinity up to 2, and from 2 to infinity. All right, so how does this actually help us analyze graphs of functions? What we can do is try and find some local extrema. That's what we're really going to focus on here. If you don't remember what extrema are, these are just local maximums and minimums. So I'm just going to draw a couple of pictures, and we'll kind of point out the local maximums and minimums, talk about what they are, talk about what they mean. So a local maximum and minimum, there we go. These are the biggest or smallest points, but what we mean by local is just that they're the biggest or smallest points around. Not overall, but around. So notice right here, we've got like a peak in our graph. That's the biggest point compared to the ones around it, so we'd call that a local max. Similarly, we've got a little minimum right here because it's lower than all the points in its little circle, in its little neighborhood. That's actually what we call that. And then this one over here, we might look at and say there's another local max. Now, the difference between local maximums and absolute maximums and local minimums and absolute minimums is that for a local extreme point, maximum or minimum, it has to either be the biggest y value or the smallest y value in the points close to it. For an absolute maximum or absolute minimum, it has to be the biggest y value out of all of them or the lowest y value out of all of them. So we could say that while all of these things are local extrema, this one is an absolute max because it's the tallest point overall. This one over here is still a local maximum. Notice that this one isn't actually an absolute minimum. It's the smallest of the local extreme points, but because our function goes down forever, there are no smallest y values. So we're going to focus on just these local extreme points here, the maximums and minimums. There's lots of different ways that we can draw these things. There's lots of different pictures that we can do to pick out these local maximums and minimums. Sometimes people will call them like vertices, like the vertex of a parabola is like a local maximum or minimum. But most of the time now, we're just going to refer to these as local extrema or maximums or minimums or something like that. So the main key here is that if we have a function and we look at a point on that function and it's a local maximum or a local minimum, then we're guaranteed that the x value that it occurs at has to be a critical number. It has to be a spot where, again, our derivative is equal to 0 or f prime of c does not exist. So as long as we have an actual point and it's a max or a minimum, then we're guaranteed that it happened at a critical point or a critical number. Let's just draw them and see what's going on here. So we could have something like this. where there's a local maximum right here. And sure enough, horizontal tangent line. If we flip that thing upside down, it'll work as well. Notice, though, that we could have a sharp corner. This point here is a local minimum, and the derivative doesn't exist. There are no other ways of drawing local maximums or minimums except for this picture and the version of it flipped upside down, or this picture and the version of it flipped upside down. Maybe we could like change the way that it approaches that sharp corner, but it's either going to have a horizontal tangent line or a sharp corner. So that's why critical numbers are going to be important. We're going to use those critical numbers to try and find our local extrema. Now notice it said if we have a maximum or minimum, then it must be at a critical number, but the opposite isn't necessarily true. Not all critical numbers are local maximums and minimums. So it's almost like every square is a kind of rectangle, but not every rectangle is a square here. Every critical point is not a maximum or minimum, but every local maximum or minimum are critical points. A little bit weird, but we'll keep an eye on that. So here's how we find them. We're going to use the derivative to find these critical points, and then what we can do is try and analyze those critical points to see if they are local maximums or minimums. So we can use a sign chart to do this. So if we've got a critical point, again, the function is defined, it's in the domain of our function, and either our derivative is equal to 0 or the derivative doesn't exist, then what we can do is use a sign chart to classify that critical point and see if it's actually a local extrema. For instance, let's say we've got x values, we've got some intervals here, I don't really care what they are. Maybe I'll make this a little cleaner. So we've got our critical point, and we're going to go from that critical point up to some other value. I don't care what it is. And we've got some interval up to our critical point. The reason I don't put infinity and negative infinity here is that maybe we've got more critical points. I don't really know. These are our x values. If the derivative goes from positive to negative here, that means our function increases and then decreases. Similarly, if we go from some x value up to our critical point, and then our critical point up to some other x value, and our derivative goes from negative to positive, that means our function is decreasing and then increasing. What this tells us is that here we have a local max at this x value. Maybe I'll say at x equals c. And here we have a local min at x equals c. These aren't the only options. It's possible that we have something where around this critical point, our derivative is positive and then positive, meaning our function increases and then increases. Or the opposite case could be true. Well, it's hard drawing all these intervals so often. We could be negative, and that's supposed to be a c here. And that would mean our function would be decreasing and decreasing, just like we found in our examples. Both of these are neither maximums nor minimums. It's easy enough to draw a picture of what's going on with each of these sign charts. Here, if we increase and then have a critical point and decrease, that means we either are looking like this, or we could have a sharp corner critical point, like that. Both of those have a local maximum. For this one, we look like the right side up parabola or a little sharp corner. And for this, if we're going to increase and then have a critical number and increase, we could either do something like this, where we increase, level off for a second, so we have a derivative that's equal to 0, and then increase. Or what we could do is something like this. Increase, vertical tangent line, and then increase. And these ones are just the upside down versions of that. Decrease, level off, decrease, or decrease, vertical, decrease. So these are the kinds of critical points that we have, and what we'll notice is that these two cases with these sign charts are local maximums and minimums. So if we want to find local maximums and minimums, all we need to do is build that sign chart, and then we can just analyze it using this test. So let's go ahead and do it. For this function, if we want to find the critical points, find the maximums and minimums, and then sketch a little bit of a graph, what we can do is first find the derivative. 3x squared minus 12x plus 9. And then if we want to find critical points, we have to find partition numbers. We have to find the values that are going to either make this derivative equal 0 or make it not exist. So, two options. Are there any x values that make this derivative, this 3x squared minus 12x plus 9, not exist? There's an easy answer to that. This is a polynomial, and way back when, we said that all polynomials are continuous, and that meant that all the x values have a y value, because that's part of our definition of continuity. Since this is a continuous everywhere function, we know that all these points are in the domain, and so of that derivative, and that means that our derivative will never not exist. Kind of a weird double negative there. So there's only going to be one type of critical point. It's going to be when we set this thing equal to 0. Now that's only because this is a polynomial function. But we can go ahead and see if we can solve this. We can factor it. I'm going to factor out a 3. Now I've got x squared minus 4x plus 3. And now we've got to factor this. Looking for two numbers that multiply to get 3, add to get negative 4. X minus 3, x minus 1. And now it's really easy to see what our partition numbers are. 3 and 1. So we can say our partition numbers of the first derivative are x equals 1 and 3. Now, take a minute, pause the video, and ask yourself, are these critical numbers of our function? Hopefully you're back, and hopefully you found out that, yeah, they are. Because the check that we have to do is to see if our function exists at these points. If you plug 1 into your function or 3 into the function, and when I talk about it, I mean this function here, then they both exist. These are actually points on our graph. That means they're critical. So both are critical. So we've answered that part of our question. Now if we want to find a local max and a local min, what we need to do is set up a sign chart. So for our x values, we're looking at intervals from negative infinity up to 1, then from 1 up to 3, and then from 3 to infinity. On each of these, we're going to check the sign of the derivative here. So go ahead, pick test values from each of these, maybe like 0, 2, and 4. Plug all of those into the derivative and see what kind of answer you get, positive or negative. I'll wait, give a shot to that, see what you find. All right, you should find these as your signs. Positive, negative, positive. What that means is that your function increases, decreases, and increases. Now, we can go back to that first derivative test and notice that in between here, when our function increases and then starts decreasing, that means we've got a local max. And at the bottom here, when we decrease and then increase, we have a local min. So that's at this x value, and we need to find the y value, f of 1. And over here, we've got a minimum at x equals 3, and the y value, f of 3. Go ahead and plug those in, and you can see what those points actually are. But then we can go ahead and start labeling everything here. So critical points. Let me flip back and forth a bit. We said 1 and 3 were our critical points. There was a local maximum at here at the x value of 1, and f of 1, let me just write this up here. That's going to be 1 minus 6 plus 9 plus 1, negative 5, positive 4, 5. Cool. Hopefully that's right. We've got a local minimum here at x equals 3. And we need to find the y value that goes with that. 3 cubed is 27 minus 6 times 9, that's 54, right? Plus 27 plus 1. 27 minus 54 is negative 27. Plus 27 is 0, and that's going to be 1. It's kind of nice. And now we can put the intervals of where our function is increasing and decreasing. I don't think I asked for that, but we may as well just put it in there. This increases from negative infinity to 1 and from 3 to infinity. And it decreases from 1 to 3. Now, notice that these two things are points, x comma y, whereas for these ones, these are intervals of x values. That's a huge distinction that we need to kind of focus on. We need to point out. It's really easy for people to get confused about what these actually mean. But these two things are points. These two things are intervals. Maybe you know what I'm going to do? I'm going to put that on the other side here, just so it's not in the way. Points, x, y, intervals. All right, so now what we can do is draw our graph. So let's see if I can sketch this thing pretty well. I'm not going to use a scale or anything like that. I'm just going to give a shot to what this might look like. So here we have a maximum at, you know what, I need to move this y-axis a little bit over because I don't really need to do much on the negative side. There we go. Now I'll have more room to draw it pretty well. So we've got a local maximum at 1, 5. Let's put that here. We've got a local minimum at 3, 1. Let's put that here. Then we need to increase up to this maximum. Then we're going to decrease down to this minimum, and then we're going to increase. And we might remember that both of these critical points are ones where the derivative equals 0, meaning both of these, if we put this in there, that might give us a hint at what this actually looks like on the graph. We're going to have some horizontal tangent lines here. So when we draw this thing, it's going to look like this. We'll level out for a second, come down. Oops, let me fix that. That's not a very good picture. Here, there we go. Go horizontal for a second. Same thing here, and then we'll keep going. So we've got these nice horizontal tangent lines, and that should be what our graph looks like. Cool. So the first derivative tells us a lot about slope. We can use that to find local maximums and minimums, intervals where our function is increasing and decreasing, all that kind of stuff. You're going to have a bunch of functions that you're going to want to analyze. Take a while to go through those. Be careful to check and see if the points that you're looking at are actually critical points, if they're in the domain of your function or not. And then hopefully you'll get some decent sketches of some things. Jump into those practice problems in the text. I think they're really helpful for getting a handle on this because there's a lot to juggle here. Good luck.